This is the first in a series of videos on trigonometry. In this video, we'll look at the primary trigonometric ratios, the inverse trig ratios, and special triangles. So first we need to remind ourselves about the primary trigonometric ratios, sine, cosine, and tangent, and recall that those refer to ratios of the side lengths of a right triangle. So if this is a right triangle and we define this angle as theta, then the side opposite theta, we name the opposite side, the side next to or adjacent to theta is the adjacent side, and of course the hypotenuse, the longest side, the side opposite the right angle, we call the hypotenuse. And now sine theta is the ratio of the length of the opposite side to the hypotenuse. Cosine theta is the ratio of the length of the adjacent side to the length of the hypotenuse, and tan theta is the ratio of opposite over adjacent. So each of these, sine theta, cosine theta, and tan theta, refer to ratios of side lengths. And some people like to remember these relationships with the mnemonic SOHCAHTOA, SOH for sine being opposite over hypotenuse, etc., etc. Now, adjacent and opposite, as we just looked at, are defined relative to the angle specified. So this is the same picture that we just saw. If this angle in the bottom left is theta, then side BC is opposite and side AB is adjacent. But if we move theta up into angle C, then side AB becomes opposite and side BC becomes the adjacent. So just something to remember from your previous studies. Hypotenuse will always be the same. So let's take a look at an example. Given this triangle, find the ratios sine theta, cosine theta, and tan theta. Well, if this is theta, then 5 is the opposite side, 13 is the hypotenuse, and 12 is the adjacent side. Therefore, sine theta, which we said is equal to the opposite side over the hypotenuse, becomes 5, the opposite, over 13. And because sine theta is a ratio, that's it, I'm done. I'm just looking for a fraction or a ratio in that form. Cosine theta, we said, is equal to adjacent over hypotenuse. So hypotenuse is still 13, but this time the adjacent is 12. And tan theta is equal to opposite over adjacent. So opposite is 5, and adjacent is 12. Notice, incidentally, that if we take sine theta and divide it by cosine theta, we'll get tan theta. Sine theta divided by cosine theta is equal to tan theta. That's a relationship that we'll see again as we go further. If you take 5 over 13 and divide it by 12 over 13, 5 over 13 divided by 12 over 13, you'd have to multiply by its reciprocal. You get 5 over 12, which is tan theta. So sine theta over cosine theta is tan theta. Here's another kind of basic question that you can be asked to do with the primary trig ratios. Given this triangle, find this length given by x. So if this is the triangle and this is 40 degrees, and we've got the opposite as our missing side, the hypotenuse is the side given to us. So because we have opposite and hypotenuse involved in the question, we're going to use the sine ratio. So sine of 40 degrees is the ratio of the opposite side to the hypotenuse. So in this case, that's going to be equal to x over 8. We want to isolate x, so we're going to multiply both sides by 8. Therefore, 8 sine 40 is equal to x. And at this stage, you'd plug this into your calculator, making sure that your calculator is in degree mode. And you get x is approximately equal to 5.14. So we found the side length of x by rearranging and using the sine ratio. Now, always remember that while theta is an angle, sine theta, cosine theta, and tan theta are ratios of side lengths. They're not angles at all. That's a common mistake that people make at first. So just remember, sine theta, cosine theta, and tan theta are ratios of side lengths opposite over hypotenuse, etc., whereas theta is an angle. Okay, another thing that you need to know about are the special triangles. So there are two special triangles that you need to know about. One is an isosceles right angle triangle, and the other one we're going to derive from this equilateral triangle. So if we start with an isosceles right triangle and define one of the equal length sides as having side length 1, that means that the other one has to have side length 1 as well. And if we use the Pythagorean theorem, we can work out that the hypotenuse has length square root of 2. Now, if this is an isosceles right triangle and this is a 90-degree angle, these two angles have to be equal, and because they must add to 90 to make up the 180 in the triangle, each of them have to be 45 degrees. So now that we've drawn this triangle, we can use the special triangle for its purpose in trigonometry, and that's to help us recall the sine, cosine, and tan ratios of specific angles. Now, let's pick this angle in the bottom right. If we want to use that to work out the sine ratio of 45 degrees, that means the ratio of the opposite side to the hypotenuse for 45 degrees. And we can see if this is the angle, this is opposite, this is hypotenuse, so the sine ratio is 1 over root 2. And because it's an isosceles triangle, the cosine ratio adjacent over hypotenuse is also going to be 1 over root 2. And the tan ratio, which is going to be opposite over adjacent, is just 1 over 1, which is 1. So sine 45 is 1 over root 2, cos 45 is 1 over root 2, and tan 45 is 1. From this equilateral triangle, we can derive the sine, cosine, and tan ratios for 30 and 60 degrees. And to do that, we're going to divide down the middle here and make two right-angled triangles. If I cut this bottom line at the midpoint, that means that this line segment has length 1. Now again, using the Pythagorean theorem, we can work out that this height here has to be root 3. Also, given that it was an equilateral triangle to start off with, this, which is one of the original corners, must have been 60 degrees because the three corners of the equilateral triangle had to add to 60. And this top one was cut in half, so it's 60 divided by 2, or 30 degrees. Now again, we're going to use just this little right-angled triangle to work out the sine, cosine, and tan ratios of 30 and 60. So if we start from 30 degrees, opposite over hypotenuse is sine, which is 1 over 2. Adjacent over hypotenuse will give us cosine, that's root 3 over 2. And the tan ratio, which is opposite over adjacent, will be 1 over root 3. Now if we switch angles, for 60 degrees, sine is going to be, again, opposite over hypotenuse, which is root 3 over 2. Cosine is going to be adjacent, which is now 1 over hypotenuse, which gives us 1 over 2 in all. And tan of 60 degrees is going to be opposite root 3 over adjacent, which is 1. So tan 60 is just root 3. So the special triangles allow us to work out all of these ratios for 30, 45, and 60 degrees. We can also summarize them in a table like this, which you might find easier to remember. So sine of 30 degrees is a half, cosine of 30 degrees is root 3 over 2, and tan of 30 degrees is 1 over root 3. Again, remember we said tan theta is equal to sine theta over cosine theta, and you can see that relationship here. 1 over 2 divided by root 3 over 2, you'd flip this and multiply and get that. Both sine and cosine of 45 degrees are 1 over root 2. And if you divide this by this, you would get 1 because they're equal, and indeed we saw from the triangle that the tan ratio of 45 degrees is 1. For 60 degrees, we got that the sine ratio is root 3 over 2, and the cosine ratio is 1 over 2. Notice that these are the reverse of the sine and cosine ratio of 30 degrees, and the tan ratio was root 3 over 1, or root 3. Now let's review the inverse trigonometric functions, sine inverse of x, cos inverse of x, and tan inverse of x. And they're written like this with the little -1. Remember from when you studied function notation that if you're talking about a generic function f of x, then f with the little -1 means the inverse function of f of x. In other words, the function that undoes whatever the function f of x does. The same thing applies here. Since sine of x is a function that takes an angle as its input and gives a ratio as its output, sine inverse of x is its inverse function and will do the opposite. In other words, if sine of 30 degrees equals a half, which it does, we can write that like this. Often it's helpful at this stage to put brackets around the 30 degrees to separate out the name of the function, the sine function, from the input, just as we did with function notation where f is the name and x is the input. So sine of 30 degrees is equal to a half. The sine function is taking an angle as its input and giving us a ratio as its output. So the sine inverse function is going to link the same two numbers, 30 degrees and a half, but do it in the opposite order. So sine inverse of a half takes a ratio as its input, a half, and gives an angle, 30 degrees, as its output. Again, 30 degrees and a half are linked, but whereas the sine function is taking 30 degrees and giving back a half, the sine inverse function is doing the opposite. So to summarize, the sine function takes an angle as its input and gives a ratio as its output. And we can use the same example as above, sine of 30 degrees is equal to a half. Conversely, the sine inverse function takes a ratio, like a half, as its input and gives an angle back as its output. So sine inverse of a half is equal to 30 degrees. And I could have put brackets around this 30 degrees as I did with the half to separate out the input from the name of the function. Now, just as with f of x, when we have a little -1 on a function, it doesn't mean reciprocate it. So with f inverse of x, you probably learned or you recognize that that does not mean the reciprocal of the f of x function. It means the inverse function. And similarly, because sine of x is a function, the same thing applies. Sine inverse of x means the function that does the opposite of sine of x. It doesn't mean the reciprocal of the sine function. And we'll see that there's another name for this function that we'll learn about in an upcoming lesson. Okay, so let's do a couple practice questions. First one, tan of theta is equal to 1 over root 3. We're being told that theta has to be between 0 and 90 degrees, so those are the acceptable values for our answer. It has to lie somewhere in there, and we're asked to find theta. So all this is asking is, what is the angle theta that's associated with a tangent ratio of 1 over root 3? And if we look back at our special triangles, we can see that an angle of 30 degrees has a tangent ratio of 1 over root 3. When your angle is 30 degrees in a right angle triangle, the opposite over adjacent ratio is 1 over root 3. So all we need to do is look at our special triangles, and we get theta is equal to 30 degrees. Here's an example of one that you can't do using special triangles. Here we're given a right angle triangle. If this is theta, this is the adjacent side, which is 7, and this is the hypotenuse, which is 11.5. Because we have adjacent and hypotenuse, we know we're going to be using the cosine ratio because the cosine ratio is adjacent over hypotenuse. So cosine theta in this case is 7 over 11.5. And we want to get to an answer of theta is equal to something, and we'll get theta is approximately equal to something because we're going to use our calculator. So we want to undo this cosine function to isolate the theta on this side. So what we're going to do then is we're going to take that whole function and put it into the cos inverse function. Because we did that to the left-hand side, we need to do the same thing to the right-hand side. So what I'm doing in this step is I'm taking the cos inverse of both sides of the equation. Cos inverse and cosine undo each other, so I just end up with theta. This side, I'm going to have to plug into my calculator. So this gives you an idea of why it's important to recognize that the cos inverse function undoes what the cos function does. So if I plug this into my calculator, I get an answer of about 52.5 degrees, telling me that theta, this angle, is 52.5 degrees. So that ends this first lesson on Introduction to Trigonometry.